In the last lecture, we talked about change of basis, unitary operators. So we define a unitary operator to be an operator U, a linear operator, that satisfies the following property. U times U dagger is U dagger U equal to identity, right? What is U dagger? It's the Hermitian conjugate, right? It's the transpose followed by element by element complex conjugation. Okay, a question. If any of you are math oriented, what is, if you only have this relation and not the other one? Could you have only this relation and not the other one? Yes, we can. What is such an operator called? No, an isometry. So think about how you could satisfy this relation, or I don't know, for example, this relation and not the other one. With everything you know, like 2 by 2 matrices, you could construct such examples. All right, good. So these are unitary operators. We define them. We said that they play a major role in physics. And basically the role that they play is changing the frame, changing the perspective, or we said is going to be related to symmetries, as we'll see in part 3 of the course, later in the course. So there was one important theorem that we discussed. The theorem says, given two orthonormal bases A and B, kets A and B, that corresponds to, well, I haven't written the rest of it, but you know the rest of it, that correspond to Hermitian operators capital A and capital B in my notation, right? You sometimes can put hats on them if you want. These are observables, right? These are Hermitian operators. We know that their corresponding eigenkets are orthogonal, right? What else do we know? Do we know about them? The eigenvalues are real. Given a pair like this, then there always exists a unitary that sends these vectors to these vectors one by one, right? So there always exists such a thing. So a quick question. So let's say there are two of these guys, ket A1 and ket A2. There's a unitary that will send this to ket B1, ket B2, right? But there could also be a unitary that flips the two sides, the two, right? That's also a unitary, because I didn't tell you, there's no canonical way of calling this the first ket, this the second ket. There's actually a unitary that will send ket 1 to just same operator, but swaps the eigenkets. So this operator shuffles the rows and the columns of the matrix. What's a simple example of this operator? Sigma x, exactly. Pauli matrix X. What does it do? It sends this to that, right? That's sigma x. All right. Unitarily equivalent observables are a pair of observables that could be written as A is U, B, U dagger. We said that they have the same eigenvalues, but they have different eigenvectors, so they're rotated, right, with respect to each other. All right. Any questions so far? So let me test your knowledge of this. We talked about a projection operator. What was a projection operator? A projection operator, an operator P is a projection operator if it satisfies two properties. First, it's Hermitian, right? Second, it squares to itself, right? Pi is pi dagger, that's property 1. Second, it satisfies this, right? Based on these two relations, can you tell, this requires some knowledge of linear algebra, what are the eigenvalues of this operator? what can a projection do when it acts on a vector? It can kill it, right? It can project it out. That means eigenvalue 0. Or it could leave it invariant, which is eigenvalue 1. Those are the only possibilities, 0s and 1, right? Now, an interesting thing is that, so any pair of projections would constitute an example like this, right? Any pair of projections, they have the same eigenvalues, but their eigenvectors do not match, right? If they have the same dimension. So that's an example to think about. For example, well, think about constructing examples of this with projections. What's another trivial example of this that we've seen already? What are the operators you know in the case of spin half particle? Observables. Yeah, sigma x, sigma y, sigma z. They're all unitarily equivalent. Why? Well, we have this because they have the same eigenvalues, right? Plus minus h bar over 2. All right. We also define a trace. Trace is, there are many ways to define it. Perhaps the linear algebra way of defining the trace that you have seen is the sum of the diagonal elements. It could also be written for a self-adjoint operator, for a Hermitian operator, it could also be written as a sum of the eigenvalues, right? Another way of defining it is that trace is using this equation. Trace of the commutator of any pair of operators is 0. This uses the cyclicity of the trace, right? Cyclicity means this. Cyclicity means if you have x and y, you can move this forward. So if there's like x1, x2, all the way to xn, you could bring this over here and push all of these guys forward. So x1 all the way to xn minus. This is cyclicity. Cyclicity is enough to define the trace. All right, it's independent of the basis. That's why we could write such a definition. Well, this is not really a definition. It's a cheat because we already know this is the definition. We talked about the eigenvalue problem. Eigenvalue problem, this is in the notation of Sakurai. I will move back and forth between the two notations just to make sure that you guys have seen both, because if you pick a random paper or book, it might be using different notation. So this is an operator, capital B, acting on its eigenket, right? This is an observable, is BB. This is called an eigenvalue problem. Just how do you solve the eigenvalue problem? The thing that you do know is the operator, the matrix B. What you want to solve for are the eigenvalues and eigenvectors. To find the eigenvalues, you first write down this equation. Determinant of B operator minus B identity is 0. This is called the characteristic equation. You solve for this and you'll find also there will be a bunch of solutions to this equation. Those are going to be your eigenvalues. To each eigenvalue, there corresponds an eigenvector, and this is a system of linear equations that you can solve and find the corresponding eigenvectors. Good? Any questions? This is very crucial. This is very important. I know that I'm not teaching linear algebra. I'm just going over it. So if this is unfamiliar, you absolutely have to fill in the gap. You have to study it by yourself. I'm happy to. All right. For physicists, for this course, the set of eigenvalues, actually, let me be a little bit more rigorous, of an observable. Let's call the set of eigenvalues of an observable its spectrum. An observable is Hermitian, therefore spectrum is always real. Good? Any questions? So far we only really considered operators with discrete spectrum. For example, the spin, right, had two possibilities. We said that the operator is quantized, right? Plus minus h over 2 were the eigenvalues. But in quantum mechanics, sorry, there are also observables with discrete but infinite number of eigenvalues. Any examples? Harmonic oscillator, exactly. Or like the angular momentum around the hydrogen atom, right? Hydrogen atom. You could have arbitrary large spin, or you could have observables that have continuous spectrum. So, which means that basically the spectrum is like it's not a set of points. It's not countable. For example, it could be an interval, right? Any value in some interval, or it could be any positive number. As an example of these operators, we mentioned that momentum operator is an observable, self-emission, and its eigenvalues are the momenta of the particle. And if a particle is moving freely, a free particle moving in space, an empty space will have continuous spectrum. Its eigenvalues could be from minus infinity to infinity. How would you change the example I just gave you to make it a discrete spectrum for the momentum operator? You've already seen this, I think. A free particle in infinite space has arbitrary momenta, right? It could be the spectrum momentum is continuous. Well, how should I change the problems for this discrete? You could put it in a well, but a simple way of doing it is that put the particle on a circle for analysis. No? If you have all right. Put it on a circle. If these comments are for your knowledge, I think as physicists, you will have to think a little bit besides this as well. If you have a circle of radius r, what are the momenta that it can support?
You're saying that's
well, if you view it as, yeah, you call it angular momentum. You could call it angular momentum. This momentum. Yeah, you could call that. It's 2 pi n over r. I recommend, I don't know how many of you guys have taken, yeah. These examples are important for physics. All right. Any questions? So here's a table of analogy comparison. So I remind you again, Sakurai's notation is they use the letter C or whatever it is without the prime to mean an operator. I was using capital letters, or sometimes I use hat to make sure that it's all clear. And I'll use all these notations simultaneously just to make sure that you guys get used to it. I'll try to suppress Sakurai's notation. It's less common, but it's a text you're reading, so you need to know it. All right, so in the case of discrete is this column. An operator A, as Hermitian operator, will satisfy the following eigenvalue problem, and the corresponding Ketz form on an orthonormal basis. If you have a momentum operator, for example, PZ, the Z component of momentum, it will satisfy this equation, right? In flat space, and the values of PZ would be continuous. We had the orthogonality or orthonormality relation, right? A prime and A double prime is the Kronecker delta. That here becomes a Dirac delta. Everybody's comfortable with Dirac delta? I'll try to include an example, a homework problem on Dirac delta. You've seen it, right? Well, okay. I should not say who hasn't seen it. All right. We had the resolution of identity, right? That we wrote like this. There is an analogous statement as an integral for the continuous case. we took an arbitrary vector and expanded it using resolution of identity in some basis, right? You could do an analogous thing here for an arbitrary ket. What is this operator? Ket A prime, A double prime, A prime. What is it? Is it Hermitian? Yes. Does it square to itself? Yes. So it's an example here. So it's eigenvector. Eigenvalues are zeros or one and one. What is this one eigenvector? Ket A prime, exactly. What is the zero eigenvector? Anything orthogonal to A prime, right? Good. Questions? We had the conservation of probabilities. The probabilities will have to sum up to one, right? Recall from the did I call it Born's rule? Maybe I did not call it Born's rule, but Born's rule is basically a statement that this matrix element square is the probability. The sum of these PAs have to be one. PA is the probability. PA prime is the probability of the outcome A prime, right? There's an analogous statement in the continuous variable case. And then we also have these type of relations that we've seen before. Good. Questions? So now we're gonna build on this example of momentum and come a little bit closer to physics. So most of what I said so far was motivated by the spin example, right? The spin of a silver atom, which was a discrete which was a quantized observable, and it had discrete values plus h bar over 2 minus h bar over 2. Let's build a little bit more on this idea of continuous variables and connect observables with continuous spectra and connect it to physics. So another example that you are very familiar with continuous spectrum is the x hat operator, the position operator, right? So the position operator is the thing that is a Hermitian operator. It will have eigenkets which are not normalizable. They are delta function normalizable. Good? Everybody is with me? You understand these words? Good. I can take an arbitrary ket psi and expand it in the eigenbasis of the position operator using resolution of identity, and I obtain integral from minus infinity to infinity if it's on a line, let's say one-dimensional line, dx prime, ket x prime. This bracket has a name in quantum mechanics. It's called the wave function in position space. Now you already see you could generalize and say you took any ket alpha and expanded this way. This coefficient, this matrix element, was the wave function in the A eigenbasis. Psi of x is the wave function in the x eigenbasis. Psi of p would be the wave function in the p eigenbasis. More generally, if A primes are the eigenkets of an observable A, this is psi of A prime is the wave function in the A eigenbasis. All right. If we could measure position perfectly, then we would describe the following thing. This is what we said we're going to use for describing measurements in quantum mechanics. You have some initial ket psi. You read off some eigenvalue x prime, which is the value, the position of the particle, and then the measurement throws your state into some ket, the corresponding ket x prime, and then this is the probability density corresponding to this. Right? This is not a probability, it's a probability density. I should have d of x here. D of x prime. But this is an idealization. We said that in practice, any detector will have finite resolution. So what actually happens is that even when you think you have prepared an eigenvalue, eigenket, you have what you have prepared is some sort of a distribution, or let's say sum over kets with some range of x prime, right? Some tiny error bars. So for example, if you had a particle and if you wanted to measure and find the particle position to be here, right? If you read x prime 0 as the eigenvalue, right? This is x prime 0. But you have error bars. So it's unphysical to say that your state after the measurement is this. Because you have error bars of some delta x, for example. So the right thing to do is that you have to integrate from some x prime minus delta x, x prime plus delta x prime, maybe over 2 or something, and then you will have these guys, and you have to normalize it, right? Corresponding normalization. The fact that the probabilities add up to 1 is a statement that the wave function, right, squared, which is a probability, integrated will give you 1, right? This is the statement that if you have a particle on a line, the particle is somewhere, right? If you integrate or add up the probabilities of the particle being anywhere, they add up to 1. So the particle is somewhere. Any questions? In higher dimensions, we're going to have a whole bunch of these position operators, x hat, y hat, z hat, or in Sakurai's notation, x, y, z. We do experiments. There's no way of a priori knowing this. We do experiments similar to what we did with Stern-Gerlach, and we discovered that you could simultaneously measure the x position, y position, and the z position. So we have to model them using commuting operators, observables. Therefore, this is a legitimate notation. So we could actually use the notation of ket vector x prime, because as a vector, it has all the 3 components. And these operators commute. So this is Sakurai notation, but hopefully you guys recall this. All right, I'm going to make a pause. Are there any questions so far? So what have we said? We talked about operators with continuous spectrum, and we have 2 examples of it so far: position and momentum, right? On a line. We're going to relate them in a second. But for those of you guys who are a physics major, I absolutely encourage you to think about the example of a particle, same example of a particle on a circle. Position has a continuous spectrum. Momentum is no longer has a continuous spectrum. Has discrete spectrum. It's just a property of Fourier transform. A lot of the side comments that I make are for you guys to think, right? If you're not interested in them, of course, feel free to ignore them. Any thoughts, questions, comments? Now that, yeah.
You made a comment in the beginning of the course about like constantly infinite, uncomplete infinite.
Yeah.
Like what that corresponds to physically, or are there being special about uncomplete infinite spectrum?
Well, there's a lot that's related. Yeah, there's a lot going on. Let's see, what can I say for the purpose of this conversation now? Let's just say it this way, that when you have discrete, doesn't matter, finite or infinite, eigenvectors, your corresponding eigenvalues, your corresponding eigenvectors have finite norm, right? Have norm 1. You could normalize them. However, if you have a truly continuous spectrum, the corresponding eigenvectors are not normalizable. They're physical idealizations and would drive mathematicians off the wall by talking about them. There's a reason for that. This is precisely the physics of it, right? You could never, ever measure position or continuous variable with arbitrary accuracy. But this is not uncertainty relations. This is just like finiteness of, like the crappy devices we have in experiments. But that's just a truth about all our devices. Thought experiment, because quantum mechanics is what started and driven by thought experiments. What happens what if we had observed, we had done the analog of Stern-Gerlach for position, X and Y operators, and had found them to not commute? What would that mean? Based on what I've told you from uncertainty relations. It would mean that there's finite resolution to nature in position. You can never localize a particle anywhere. Luckily, that's not the case. But there are some reasons to believe that might be the case at very, very high energies. Yeah.
Like a smaller distance.
That was the comment that I made. There might be some physics associated with that over there. We'll come back to this actually as well. Not to this, but to phase space. I'm talking about uncertainty relations. All right, any other questions? So what is the task that I have for the remainder of this lecture? To relate two observables right? So before we talked about discrete operators, sigma x, sigma y, sigma z, when we talked in detail about how to relate them. Now you know two operators with continuous spectra, position and momentum. And my goal is to relate them, right? Let's forget about momentum for a second. What we're gonna do is we're just gonna work with position, right? Once you talk about position, because I said the magic keyword of Fourier transform, if that was cryptic, I'm just gonna explain it. Once you know about position, what you could define is, you could immediately define translation operator. What is a translation operator? It's some curly t, this is an operator that acts on the ket x prime vector and sends it to x prime dx prime, right? This is the amount by which you translate. We're going to discover the momentum operator in a bit, right? We're not using momentum at all. I can always define this operator. By the way, this is the analog of sigma x. Can you see the analogy? What is it doing? It's doing exactly that shuffling of eigenkets I talked about before. Is that clear to you guys? I said the following. I said I can have A1, A2, all the way to AN. I'm going to write them here. A1, A2, AN. I can define this shift operator right? That's going to be cyclic. It will send this guy to here, right? Now, if these were the eigenkets of position, what this is doing is translation. The fact that I'll have to do this is corresponds to the fact that if I had a particle on a circle, then the translation would do that bring it back. Good? We're good? Okay. If you have, now that you find translation, you could already see some physics in it. Could the translation operator have an eigenket with eigenvalue 1? And if yes, what's the physics of that?
There's only one.
So when it acts on this ket, it translates it makes a physical translation in position. However, nothing changes. That describes a translation invariant state, right? Good. All right, so here's a definition, and I defined an infinitesimal translation. You'll see that in a second, why I did that. All right, so as usual, perhaps the most important trick we have in our tool we have in our toolbox is resolution of identity. So let's just apply a resolution of identity in the X prime basis, because that's the only operator we have so far. So what we find is you apply this term becomes a wave function, and this is the shifted guy, right? So the first line, is that clear? So I just applied the resolution of identity. This is called the wave function. And this translation acting on ket X prime sends it here. In the second step, what I do is that, well, X prime is a dummy variable. So I could shift it by dx prime so that this becomes X prime. And now this guy becomes a minus X prime. I can really, truly shift this if these are from minus infinity to infinity. So what happened? Now it became ket integral over dx prime, ket X prime, the wave function at shifted value, but in the opposite direction. So let me pause here. Are these two lines of algebra clear? What I'm doing is I'm applying translation to an arbitrary ket, to an arbitrary state. Well, arbitrary ket. Questions?
Line 2 to line 3.
Yeah, so line 2, what I did was I first gave this guy a name, psi of X prime. Then translation acts on the eigenket. Because it's a linear operator, I could bring it inside the integral. And I had this identity that defined my operator, so this becomes here. So this is the line 2. Line 3 is I have an integral over dx prime from minus infinity to infinity of something. I can always, I'm always free to shift the variable, and the shift doesn't change the boundaries because it's a minus infinity to infinity. I'm shifting by finite amount, right? So that's what I've done. This is how the translation operator acts on an arbitrary ket. So let's look at the properties of the translation operator. We're gonna list 4 of them. Recall that the goal is to relate this to, well, I'm gonna show that this translation operator is related to momentum. This argument is very, very basic and very simple, but as a physicist, you will never get over this. Like, you constantly use these type of arguments, like in day-to-day basis, as a theoretical physicist. All right, so the first property is unitarity. Unitarity means what? Unitarity means that translation operator dagger times the translation operator is equal to translation operator times the dagger of it equal to identity. All right, let's test that. Let's just put T dagger T inside some arbitrary ket. Can you see that this is equal to 1? Do you want me to do it on the board? All you need to do is T acts on alpha, plug in this expression. T dagger, bring T dagger acts on bra alpha, takes the dagger of this relation. Sandwich them, and using the identities you have, you find that this is 1. Do you want to see it explicitly? Yeah? Okay. All right. Can you see here if I write? This is what I'm starting with. For this, I had this identity, the third line, right? So this will give me an integral over dx prime of x prime, right? X prime minus dx prime and alpha, an integral over dx prime that I'm going to write here. Right, so this line you can see. I just separate them by a large amount so that I have space for this. This will give the opposite side. So I'll get another integral. Let me call that double x prime. Double x prime. And then I'll pick up a guy like this. I'm going to write, actually, let me write it. All right, what did I do? I applied that identity to once. Once here, once here. These are linear operators, took the integrals out. Good? What is this? Dirac delta function. Which means that I can get rid of one of my integrals at the cost of replacing x prime equal to x double prime. So let me do that. So I'm going to get rid of double prime, because it's longer to write. So that gives me x prime minus the x prime minus the x prime alpha. Good. Are you with me so far? All right. These are minus the x prime and integral over the x prime. I can redefine my integration variable, right? Call this, I don't know, triple prime. Actually, let's call it x prime. You guys are mature enough with algebra that I can call it x prime. Alpha, alpha. Good? You see this? Sorry. Let me move this to the side. Oh, can I move this? Good. So what is this expression? Resolution of identity. I can get rid of it. What am I left with? Alpha, alpha. What is that? 1. Right? You want to check the other way around? Just flip them. You just have to get comfortable by with taking daggers, which I absolutely recommend you to do. Good. Actually, based on this relation, I haven't proven it's unitary. What I need to do to prove this unitary is I have to replace this with beta. The beta goes for a ride. And at the end, I end up with alpha beta. But Let's not do that. Questions? Yeah.
Sorry, can you explain why you have to take beta to prove it's unitary?
What I've shown here is that this operator, all its diagonal elements are one. Technically, because I've shown this in any basis, I've proven that this is identity. But if you want to be very, very strict, we'll put beta over there. If I've proven that this is equal to identity, what have I shown? I've shown that this operator is an isometry. If I prove it the other way around as well, I've proven it's a unitary. So I have to do the other one as well. But I trust you guys can reproduce the algebra. Good. Those of you guys who are very, very theory oriented, you can see a subtle assumption in here. But yeah, if you don't see it, forget about it. All right, so unitarity. That's property number one. Property number two, multiplication. If you multiply, so multiplying operators had the interpretation of applying them in successive order, right? Successively. If you first translate by dx double prime, then translate by dx prime, the net result should be translation by dx prime plus dx double prime. Notice that these are vectors. I can just add vectors. This is vector addition, right? That's just consistency relation. Good. There is a notion of an inversion. If I translate in a direction, I can translate in the opposite direction, and that's the inversion. So translation by minus dx prime is like the translation operator to power of -1, but because we proved that it's unitary, it's the translation dagger. Minus, yeah, that's a minus sign. Translation -1 to power of -1. Equal. Sorry. Thank you so much for asking. My handwriting is not. I should have been a real doctor, not a. All right. Zero translation should be identity. So if I take the limit of dx prime going to 0, that should be identity. This is 0 in my world. All right. How many of you guys know what a group is? So I just proved, if you're math oriented, I just proved to you that it generates a group. Can anyone name what that group is? R3. Anyway. All right. Any questions about these properties? If you want me to shut up, I can just cut out all the comments. Any questions? I want to repeat that these need not be in the same direction. Oops. Right? This is we define this for a vector. We define the vector worth of transformations, right? So this is a consistency relation. Questions? All right. I could have done the exact same thing, and I encourage you to do the exact same thing for qubit, for sigma, for these two states, plus minus. I encourage you to check all of these properties. They will go through. There's a name for that group. It's called Z2. It's a group of 2 elements. So even though I'm doing this example here for X, you should definitely try to apply it to the other example you know, which is spin. The next step I'm going to take is also similar. Yeah.
Changing the direction of spin translation.
Say it again.
Like, you're saying changing the direction of spin in the translation?
So no, the analogous thing is you have to go back to my definition, right? What did I define? I defined this translation operator as the thing that shifts this by some dx prime, right? This is an eigenket of x. This is another eigenket of x. If you have a spin, if you have plus and minus, the only thing you would define is something that sends this to this and this to this. That's sigma of x, right? Pauli x. What I'm saying is that once you take Pauli of x, we check all these properties, except for this one, because there's no limit you could take. It's not a continuous variable. What's the inverse of sigma of x? Sorry? Yeah, sigma x itself. You could tell based on the fact that it's a group Z2, but anyway. All right. So, oh, actually, sorry. There is a continuous version of that here. Never mind. We'll get there. We'll in a couple of lectures, I'll do a continuous version of it for spin. All right. So what am I gonna do next? Now that I define this operator, T, this is, by the way, Curly T. This is Math Cal T for LaTeX people. It's my attempt at doing that. So translation operator, because it's an infinitesimal translation, I'm just, actually, it doesn't matter. I'm gonna define the operator K, right? This is this relation, if you wish, is a definition. This is a definition. It's a relation that I use to define a vector valued worth of operators. Here's where the notation of Sakurai is simpler than my notation, because in my notation I have to put a ket up here as well. This is an operator. Yeah. No, the x prime here is a number because of prime. Well, it's a vector. So what is this? Let me write it down. If you want to expand this, this is K of x operator, D of x prime, plus K of y operator, D of y prime, plus in 3 dimensions, right? D of z prime. Good. Now, here's something quick for you guys to check. The properties that we just proved, these 4 properties, will imply that ket, this operator I defined, is Hermitian, and all its components are Hermitian. So this operator I just defined here, with an I here, is an observable. So is the line of logic clear? What I'm doing is I proved a bunch of properties. I define an operator K. I'm saying the properties imply that this operator K must be an observable. Yeah.
What's the math principle behind like writing in this form?
The algebra. Continuous groups. For those of you guys who haven't heard the word the algebra. All right. So K is an observable. We started with an operator with an observable X. We discovered a new observable that was naturally defined. What is this observable? The observable K generates translations, right? We're going to say generates translations. Quick question. I'm sorry, quick questions. How am I doing on time? All right, I'm okay. Yeah. Is this the only way that I can construct the form of this operator? Well, I can always do this definition, and the properties will tell me that this operator I define will be Hermitian. You're asking whether there are other operators that we naturally define. Is that what your question is? Well, they're all going to be one way or another related to this object. I claim, but I haven't explained that to you. Think of it as a trick for now, right? But the trick is extremely general. I started with one observable. Along the way, I discovered a second observable. This should look suspicious. Hopefully, you can see that, right? There's something really fundamental about quantum mechanics going on. I started with one observable and I discovered a second observable. So it's as if observables come in pairs. Can you guess where this is going? You've heard the word in physics, conjugate momentum. In physics, often we could associate to observable the conjugate momentum, even in classical physics. This is the physics of it. All right, so before talking about the physics of the K operator, let's do a quick detour and prove one extra bit of information. What is that? Well, I want to calculate. I have now two operators, right? I have the X operator and I have the translation operator. And my question is, what's the commutation relation between X and the translation operator? Notice that the translation operator is not Hermitian. What is it? Unitary. All right. So to do this, just okay. Let me say this. Every single time, pretty much almost always, you want to figure out the commutator of two operators. This is the two lines of algebra you do. This is the commutator A and B. It's AB minus BA. You pick a complete set here. You apply AB to the complete set, you apply BA to the complete set, you subtract them. This is the trick. But hopefully, based on linear algebra, we should be able to follow this line by line. So this is the, again, Sakurai notation. I keep repeating it, so hopefully it will, at some point, it will click. It took me a while, like a long time ago. Every time I open Sakurai, I still get confused. So this X, if it doesn't have primes, it's not an operator. Okay, in Sakurai's notation. I'll try to put the hats sometime. I'll remind you of the hats. So we're going to apply it in this order because this is xt minus tx. So first we're going to apply xt to a complete basis, orthonormal basis. This, by definition, just shifts the ket. This is an eigenket, by definition gives the eigenvalue. So that's the first step. The other order, first, this gives me x prime. This is an eigenvalue. I can bring it out. Then this applies and shifts it. So first order gives me this. Second order gives me this. If I subtract them, I end up with dx prime, the shifted ket. Now, because I'm interested in an infinitesimal translation. A tiny translation to the first order, I can replace this ket with the initial one. So I discovered that this commutator is dx prime. What is it as an operator? The commutator is an operator, right? What did I find the operator to be? I found it to be dx prime as a number, a bunch of numbers, multiplied by the identity operator, right? All right, very good. So now we have we have this relation. Any questions about this derivation? It means this. If you have it's just Taylor series, right? if you have a function,
So it's the Taylor expansion.
it should be Taylor expansion for vector or something. It's Taylor expansion. Yeah. Any other questions? By the way, if I'm over explaining, also tell me. It's more likely that I fall from the other side. All right, so now we have this relation. Recall what our operator K was. Plug in the definition of the operator K here. What you find is, you find that after one line of algebra, that you find the following commutation relation between the X and K operator. The commutator is I, delta Ij. The delta Ij is important. Kx generates translation in the X direction. It commutes with the Y position. You could simultaneously know about the generative translation in the X direction and the position in the Y direction, but not the same direction. All right, I'm gonna pause here. Any questions? Are there any questions? What I'm doing has Fourier transform written all over it, by the way, in case it's not clear. I'm basically teaching Fourier transform. Questions?
So why this equation can success only if X prime for a complete basis?
Oh, because of the following. If you have an operator X that at some operator, I don't know, like give me a letter, I don't know, like J, operator J, that acts on a whole bunch of X prime things, right? And it's equal to some operator letter, W. X prime. I can conclude these two are equal if and only if these guys are complete bases. Let me give an example, right? Take the following two matrices. Like, I don't know. Matrix one is this, acting on some vector, 1, 0. A, B, 1, 0. C prime, B prime. This equation is satisfied, right? But these two matrices are not the same. The reason is that as I multiply this, I get A plus B, C plus D. Oh, sorry, 0. A plus B is 0, right? So only one of them, if I only have one of them, it tells me about one row of the matrices being the same. I need a complete set worth of these guys to conclude that the two operators are equal. Thanks for asking that. Yeah. Oh, sorry, I think I messed up. It's a C that. A, there's no C. My example was wrong, sorry. Yeah, thank you. Good. So every time I said row, I meant column. All right. Thanks for asking the question. That was a good one. If I don't explain something like this, please ask. After a couple of trials, I'll get it right. All right. So now here comes some physics. So far, a lot of it was just algebra. What observables do KIs correspond to? It generates translations. So it's tempting to call it a momentum. But there's a problem. The dimensionality of it is wrong. The dimensionality of K, what is the dimensionality of K? It's 1 over length. Why? Anyone? Yeah, because I defined it as 1 minus ik dot dx. So the dimensionality of one should be the dimensionality of k dx, right? X dx is length, therefore k is one over length. Good. But momentum has dimensionality what? Momentum. It's not one over length. But it's tempting to call this momentum up to a universal constant because the argument I went through is so general. It's extremely general. Turns out that this was actually discovered in early days of quantum mechanics. There was a relation completely independent of all this algebra we went through. There was a relation that was people discovered between wavelength of a particle, 2 power lambda, and its momentum. The constant that sits in between is called, Planck constant. Oh, whoa. Planck constant. By the way, I apologize if you've seen Planck constant as h, and I'm calling it h bar. H bar is h over 2 pi. For me, it's all the same, right? 2 pi is not a big deal, right? Okay, so it's h. I think I got this right. No, maybe I got it wrong. Maybe it's h. I don't know. You can figure this out. But the point is, already you have such a constant. It's called h bar. All right. So let's put h bar here. And if you put h bar here in your definition, you figure out that now the commutator of the position and momentum is I h bar delta of ij. That you could have guessed from day one, right? If there is a commutator to x and p that is proportional to identity, we better have a dimensional full parameter in there, and we better have a dimensionality of the dimensionality of h bar action or angular momentum. So by now you've seen h bar appear in discrete eigenvalues and in continuous, in operators with discrete spectrum and operators with continuous spectrum. So this is absolutely crucial to say. In the case of discrete spectrum, how did it come about? It was just an observation. We observed that the observable is quantized and the values of the quantization parameter was h bar over 2 minus h bar over 2. Right? That was just something we saw in nature. When the operator is not quantized, like not quantized as a continuous spectrum x, a priori, it wasn't clear how there is ever going to be an h bar. But we found an h bar. Hopefully that's clear. This is a deep result about nature. I can't stress this enough. Yeah.
We're calling it h bar, but it could be some combination of other fundamental concepts. Right?
Yes. Absolutely. It's a fundamental constant for sure, based on the argument I gave you of quantum mechanics. Now you're telling me that maybe as a theoretical physicist, we're going to discover more complicated theories and then one day derive this. But I can tell you that you won't. But that's not a service course. There's a reason I say you won't, but anyway. All right, good. So now we discovered that position and momentum do not commute. They could not be simultaneously measured, which means that there's a finite resolution to anyone? Phase space. The space of position and momentum is called phase space. Is that familiar? Because if you don't know that, I should change my next lecture. Anyone knows what phase space is? All right. Okay. So it's X and P's. Yeah, the phase space is if you have an operator, classical physics, okay, any observable, you could associate canonical conjugate with. It is, I think, it's very unfortunate that the way we teach physics sometimes it's like not in order. We jump over things, and yeah, okay, sorry, I apologize. So let's go back. Let me not do the detour. So based on what I told you, you have an observable. You could associate a canonical conjugate to it, momentum to it, right? This analysis could be done in classical physics as well. Do you know how? The whole thing I told you could be done in classical physics. Poisson bracket. Have you heard of what? Oh, sorry, let me not ask that question. Do you guys learn about Poisson bracket in classical mechanics? No. Ooh, that's bad. All right, I'll try to teach it. You know, because the reason I say this is the following. Quantum mechanics, I've been saying how wacky and crazy it is. And it seems like we just took classical physics, threw it out, and redid the whole thing. But if you know Poisson brackets, maybe in 2 lectures from now, I might have to teach something in between. And we'll see that actually quantum mechanics could be connected nicely to the old arguments of classical physics. The commutator is just a change of perspective. But we'll get there. Any questions? If I'm assuming that you guys know something, please do tell me that I'm making an assumption, because I've never taught undergrad courses and I don't know what we cover here. So when I did my undergrad years ago, I learned that. So, and also Sakurai assumes that everybody knows it, which is not right. Okay, so if there's something, just send me an email. All right. Good. So now, an important consequence of non-commuting operators was the uncertainty relation. So here it is: X and P have do not commute. So the uncertainty relation sort of tells you about the fluctuations, right? The root mean square, or whatever it's called, variance. I never know which one has the square root. This observable is much larger, is larger equal to the quarter of the commutator. You just plug in the values and read it up. You find that it's larger than h bar over 4. Good. Okay. Now, I said I was making an infinitesimal translation, but what about a large translation? How do I get a large translation? Thoughts? By applying many infinitesimal translations. So if you want a large translation by some order 1 delta x, this is capital delta x, right? What you would have to do is that you would have to apply an infinitesimal translation. So this is just basically calculus. I want to move my head x to head x prime plus delta x prime. And I'm gonna do it by first taking this thing and splitting it in delta x prime divided by n, multiplying these infinitesimal guys together, n of them, and then take the limit of n going to infinity, right? So that each of these guys is infinitesimal and my analysis is correct. Good. All right, so what is that? It's the limit of, this is my infinitesimal translation. I just plugged in my definition of P of X, right? I was just assuming they're all in the X direction. I don't have to. Anyway, this limit has a name. It's matrix exponential. This identity, I'll try to, have you guys seen this identity in quantum mechanics before? It's a very, very important identity. If you want to read more about it, try to work it out yourself. Based on your knowledge of matrices, you could do it. But if you want a little bit of a help, read up on Trotter expansion. I think it's not on what. I think it's well. All right. So if you're asking what is exponential of an operator, there are various ways to answer it, but for the purpose of, for now, just take the Taylor series expansion of exponential and just plug in the operator. Good? Is the definition clear? All right. So we also learned that finite commutators commute. Finite translations commute. Why? Because momenta commute. Well, I think, oh yeah, one more thing. Now, momentum operator is a Hermitian operator. It could have continuous spectrum, for example, on a line. It will have eigenvectors that are Dirac delta function normalizable. We're going to call them ket p prime. Good. This try to prove this relation. There's 2 lines of algebra. I absolutely recommend going through these slides. Try to fill in the gaps. I don't have the time to just like literally write everything on the board. Most of it is in the book, but you absolutely recommend it. Not even looking at the book. You should be able to fill in the between. All right. Let me just finish by summarizing. So I'm going to summarize and give it a name. Canonical commutation relations. What is this all about? I said take an X operator, right? Position operator. It's a vector worth of things. It commutes with itself. I define a translation operator naturally, and then it led us to defining momentum operator, and momenta commute with themselves. However, position and momentum do not commute. The commutator is IH bar delta IJ, right? These are called canonical commutation relations. Why are they called canonical? Because in this story, it was unimportant that it was the X operator. If I start with another observable that has continuous spectrum, I would have discovered another operator analogous to P that's called the conjugate momentum, and it would have to satisfy that IH bar relation. Right? This analysis is very, very general. Good? All right. So just one thing to know for you guys, commutation relations, you know, the commutator we defined, right? The commutator of 2 operators is AB minus BA. So using algebra, we can prove those relations. They're pretty straightforward. Every operator commutes with itself. AB, commutator AB is minus commutator BA. And there's this multiplication rule. I can never remember it. I actually almost always have the Wikipedia page on commutators open because it has the list of these identities for a gazillion of these guys. I almost have it open all the time. You can tell how often I use it, right? This one is easy to remember. This is perhaps the most important one. It's called the Jacobi identity. It's a relation that holds 4 commutators defined this way. If you want to see the structure, and it looks kind of ugly, but let me show you the structure. Cyclicity is the idea. If you have A, B, C, right? What we're gonna do is, if you have A, B, and C, you could apply a cyclic shift, right? You could apply another cyclic shift, which is going to give you A, B, C, right? So, I think, yeah, these are all cyclic. Oops, oh, that's not true. B, C, A, yeah. So what I'm doing is that I'm shifting this here, here, here. right? Here. Basically, the idea is that write commutators, two of them, and add the cyclic rings in between. This is called the Jacobi identity. It's extremely important. I cannot say this. No. It's extremely important. Jacobi identity. If you don't know the other ones, well, the other ones are trivial. But this one is extremely important. All right, I'm just going to stop and summarize. So what did we do today? We basically said that if you have an operator with a continuous spectrum, right? We like X, we found that we could naturally define a translation operator that was unitary. It was yeah, we proved a whole bunch of properties for it. It led to the definition of a momentum operator, and it also, we discovered along the way that there is a constant H bar sneaking in to quantum mechanics, even for continuous operators. Any questions? Yep. They are already.
They are?
Yeah. I posted them like half an hour
Oh.
before the class started.
Okay.